In 1850, William Rankine coined the phrase conservation of energy, which is now one of the most powerful laws in physics. This is one of the fundamental rules in which the universe operates. The law of conservation of energy simply says energy cannot be created or destroyed. This is shockingly useful. It means that if you have a closed system that's not being influenced by other things, the total energy, all the different types we talked about in the last video, if you could account for all of it and add it all up in that system, that number is never going to change. And that is really useful, especially if we deal with some kind of very simple system, like, say, a ball rolling down a hill. This is a problem we explored talking about Newton's laws. Let's make it a whole lot easier. Check this out. You've seen this problem before. Free body diagrams, tilted axes, all that stuff. Let's change it up. Let's make the hill curved so you can't solve it in the ways that we have in the past. What then do we do? Energy is conserved, so take all the types of mechanical energy at the top of the hill and set them equal to all the types of mechanical energy at the bottom. This is even easier than it looks. At the top, there's no speed and there are no springs. At the bottom, there's no height and there are no springs. So this becomes the initial potential energy due to gravity becomes the final kinetic energy. This looks different depending on which class you're in. From here, just substitute in each type of energy and solve for V. That was so easy it should annoy you that I didn't teach you this back in September. I have my reasons. Now, if you were paying good attention, you realize that I said, in a closed system, energy is conserved. What if it's not a closed system? What does that mean? It means that work has come in from outside the system in order to modify the energy, change the energy of the system itself. The example I gave last video of the car rolling this way. If you push it from behind, you're doing work on it to give it energy and speed it up. You run around to the front and you push on it, you do negative work on it to slow it down. Again, do not try that. So anyway, the work energy theorem says if there is work coming from outside the system, or if there is work that is converting mechanical energy into other types of energy, then it's not quite as simple as that previous example we just gave. So we have to modify it. If you look on your reference tables, you see these little additions. They're extremely important. Work is the change in energy of a system. How much work you do is how much you've changed the energy. I like to write it like this. You don't see it on the reference tables this way, but initial energy plus or minus any work done equals final energy. We're going to use that like crazy this year. And from now on, if you're really scratching your head and you're not sure how to do a problem, I want you to go to this first. It won't always work, but it works so often. So let's look at another problem that would have been kind of annoying to do prior to this concept and see how easy it is. Suppose we had a cart with an initial velocity and we got behind it and we pushed it with a certain force over a distance. How fast is it going at the end? Prior to just now, this problem would involve Newton's laws and kinematics in order to get an answer, and would be probably a 4 or 5 step problem. Let's look at it with the work energy theorem. It starts with some initial kinetic energy. We do positive work to add energy to the system, and it ends with a different kinetic energy. From here, just substitute in 1/2 mv squared for kinetic energy, work equals force times distance, plug in your numbers and solve. Done. And there you have it. Conservation of energy and the work energy theorem combined can solve an enormous number of mechanics problems for us. They'll solve electricity problems later too. If you take AP Physics 2, they'll solve fluids problems. They are universal ideas that literally help govern how the universe works. See you next time.